All right. We're going to try this. I am recording it in case the stream decides to go down so that I can just post it later. But we are going to try to stream it. And I don't know, it's just been kind of finicky lately on getting the streams to run. Um, we're going to continue our torsion. So we're doing angle of twist today. So what I thought is we'd introduce angle of twist, the concept of it. We don't need to derive it like we did the torsional stress. We'll just go back to the variables that we started with last time, and we'll talk about what angle of twist is, the equation to calculate it, and then we'll work some problems that use both torsional shear stress and angle of twist. So we'll get some more practice on the torsional shear stress. We'll work some of these web work problems in the optional 3, assuming we can find some good ones to work. So angle of twist is the other piece of the torsion failure mode. So it could be that, like we did, it was yesterday, where we talked about an object twisting and it just shears, it just breaks in half, or maybe it yields, and either one of those are bad for the shaft that might be transmitting power, or maybe just motion or whatever, or maybe it's a spring that's twisting and you don't want that to yield or break either. So that's what we did last time, the torsional shear stress. If the torsional shear stress exceeds the shear strength of the material, then it will either yield or break, depending on which shear strength you're talking about. But it could be that it doesn't do that. It doesn't yield, but it twists to the point that whatever purpose this shaft is serving would be considered a failure if it twisted too much, but didn't yield or break. And so that's what this angle of twist is. So let's look at our screen. Yeah, I want to make sure that the audio was actually on, and it is. All right, so that would have been bad. Let's look at our screen. There we go. So torsional shear stress is what torsional shear stress is what we talked about last time. Just as a reminder. And that was tau was the torsional shear stress, equals T, the torque applied, or the torque internal to that whatever cross section you're talking about of the shaft. Remember this equation, T times C over J, this equation is not necessarily specific to a circular shaft, but whenever you put a certain value in for J, in particular, we were using J is the polar moment of inertia. And we used pi over 2 times c to the fourth minus b to the fourth. So that equation, c to the fourth minus b to the fourth times pi over 2, that equation is only good for circular shafts, hollow or solid circular shafts. So that using this part does mean that this equation only works with circular shafts. So we'll make that little note. And we went through and actually derived that yesterday. So if you want to go back and look at that, then that's why this equation, when we put pi over 2 c to the fourth minus b to the fourth, why it only works for circular shafts. You can kind of get a clue because it's got pi in there, so that's usually going to relate to something round. TC, now I put C in here. That gives us tau max because the torsional shear stress is 0 at the center of the shaft, and it's maximum on the surface of the shaft. And C is the outer radius. I could, if I wanted to, put some other number than the outer radius. I could do the inner radius, or I could do anything in between those two numbers and calculate a little bit lower torsional shear stress. If there might be some reason to do that sometimes. But a lot of times it's going to be that you want to know the maximum one, which is on the surface. All right, so that's all the stuff we did last time. So we also drew a picture kind of like this, where we had a shaft. I'm going to try and put a more perfect end on it there. Okay, and imagine, well, and it had torque applied to it, right? So let's put one torque here. Actually, let's not put the second one yet. Let's imagine that there is a line drawn here, like a straight line drawn on the shaft, on the surface of the shaft. And then when I apply the torques to it, so this is the opposing torque to the first one I drew. When I apply, oh, well, it changed my line to red, but that's fine. When I apply this torque, it starts to twist. Assuming I apply enough torque and the shaft is, small enough, then it will start to twist, and that line will do something like this. Just say that does that. So it twists across the surface of the shaft because the shaft is twisting. Now, does it look like a perfectly straight line, or has it got some ramp up and ramp down on the end? I'm not worried about that. Just in general, it has a angle. Now, it does have an angle here, there. That's not the angle of twist. That would be a shear strain type of angle. But the angle of twist that I'm interested in is if we look at the end. So if we look at this surface here, this yellow, bright yellow surface, let's look at that one. So I'll draw that surface over here as a circle. And let's say that we have, that's point A, and it's right there. And then this is point B, and it's right there. So point A was, the end of this horizontal line. I twisted the shaft and it moved up to point B. So point A moved to position B. The angle here, that's our angle of twist. And it's going to be our equation, theta equals T, which is the torque applied to the shaft, making it twist. So the torque in that section. And this is sort of similar to when we did axial deformation, where you had the equation delta equals force times length over area times modulus of elasticity. And every little section where one of those variables changed, you had to write a new equation. Same thing for angle of twist. So if I change any of the variables in the equation we're about to write, then I have to create a new section for this equation and then add them all together, just like axial deformation did. So T is the torque on that section times L is the length of that section. So here L would be this value. And, we might have to chop the shaft into a bunch of little sections, each of their own length L. Oop. Let's draw that in this color. TL over J, that's that polar moment of inertia again. So that's representing the cross-sectional area property type things. TL over JG. So G is a new thing we haven't used before. It's analogous to E, the modulus of elasticity. So remember, way back at the beginning, we created some graphs where we had strain and we had stress, sigma, and we put a graph kind of like this on there. And we said that, well, this little region is linear, and the slope E over 1 there, the slope of that straight line is the modulus of elasticity. We also use Hooke's law to relate stress to strain through the modulus of elasticity in that linear region. You can do the same thing where you do shear stress and you do a shear strain and you get a graph, same kind of graph, and that linear region is related through G, the modulus of rigidity. So it's the same kind of thing as E, except that it relates strains instead of stress, it relates shear stresses and strains instead of axial stresses and strains. So it's a number you look up in the chart, and it's smaller than modulus of elasticity. It's usually around half, somewhere around half of the modulus of elasticity. That's not a hard and fast rule. It's just somewhere in that range. And remember that a lot of times all the time, no, not all the time, but many times in our class, we will use half of the tensile strength to get the shear strength. Sometimes we use a different number because it actually tells us a number. And so that's kind of the same relationship here. So we'll have to look that up. It's a material property. So I guess I do need to find that. So we can look this up. Let me get our reference materials, material properties, and we'll look at this. It's taking a while to download. Actually, it's taking a long time to download. I'm not sure really what's going on with it. There we go. All right, so I'm looking at this. So over here in the, oh yeah, there you go. Over here in the far right column, you've got modulus of elasticity, and then right next to it is modulus of rigidity. Let's see if we can zoom in to make that a little more readable. Let's see, let's go over that way. So there they go. So you've got numbers like 29 million for, this would be the structural steel. I think the top number is wrought iron. And that's for the modulus of elasticity. Modulus of rigidity, which relates to shear, is 11 million psi. So that's the kind of things that we're going to get material properties out of some kind of chart like this. All right, so let's go back to our little problem. All right, so we're over here, and we've got our equation, TL over JG. So we've got a equation. We need to put some numbers in it and solve for the angle of twist. I will point out, I noticed the stream is getting kind of laggy. So I am recording it, and I'll post the whole recording later if you'd just rather watch that. This one shouldn't be very long. Actually, it's pretty, just as soon as we work a couple of problems, then we'll be ready to move on to the next thing next week. What I was going to point out is that theta equals TL over JG. Those units will produce radians when we're done with it. So when we're done with calculating T times L divided by J times G, we will get radians. Where should I put that? So the number you get won't be degrees. Even though we call it angle of twist, it's going to be radians, not degrees. All right, so let's set us up a simple one to just plug in the numbers, and then we'll go get some out of web work. So let's say we have a solid rod here. So it's going to be solid. We're going to put just a single torque on it. Let's say that torque is 150 foot-pounds. That's a lot. Let's say it has a outer diameter of OD equals, let's make it 1.5 inches. No, let's not use the same kind of number. Let's do 2 inches. So it's really pretty beefy rod. Let's make it metal, structural steel. And then we also need to know how long it is. Obviously, the longer these things get, the more they're going to be able to twist for a given torque. So we do need to know the length of this. And let's say that this thing, I don't know, it's like that big and 18 inches. It'll be like this. Okay. So the thing we want to solve is we want to find, so we're given this, and we want to find theta from point A to B. I haven't labeled those. We'll call this on the very end A and this on the other end B. So the angle of twist along the whole length of the shaft. equals the torque in that section AB times the length of that section over the modulus, the polar moment of inertia of that section times the modulus of rigidity for that section. So the torque in that section, we could draw our free body diagram. Remember, we want to know the torque inside it. I'm not going to take the time to draw this particular one, but the torque in that little section would just be 150 foot-pounds. And then the length of that section I've got set up as 18 inches. You do have to be careful with your units because I'm mixing feet and inches here, so we have to make sure we convert those. I'm going to put this in MathCAD so it will convert it for us. J pi over 2 c to the fourth. C is the outer radius. I have the outer diameter. The outer radius would be 1 inch to the fourth power. Minus b is the inner radius. This one's solid, so b is actually 0. And then times the modulus of rigidity, not elasticity. Modulus of rigidity. I said this was structural steel. We just looked that up, and it was 11 million psi. So I'm just checking that to make sure I didn't imagine that. Yes, 11 million psi. All right. So now we can put that into MathCAD. Let's see, where did MathCAD go? Here we go. So we have T equals 150 foot-pounds. Oh, let's make it a capital T though, because that's usually what we use for torque. L was, what is it, 18 inches. G, we used 11 million psi. TL over J, we need J, so also we need C. C is the outer radius, 1 inch. J is pi over 2 times C to the fourth minus B to the fourth, but that was 0, so we're going to leave that out. And then we can do theta equals T times L equals T times L over J times G. And the number we get, let's remember MathCAD is going to round off to 3 decimals by default, so let's give it some more. This is how many radians. So 0.018 751 radians. If I want to know degrees, then I can just type in DEG over, once I get in that little unit holder, 0.1 degrees. So don't be surprised if you had a really long piece here that's got a decent amount of torque applied to it. Don't be surprised if you get a large number of degrees. It is possible for a lot of twisting to happen. Now, just because you calculate a large number of twisting to happen doesn't mean it would actually happen, because at the same time it is generating that torsional shear stress in there, and it could be that it yields before it's actually able to twist a whole bunch. So you do have to check both of those things if you're looking for which one is going to dominate the failure mode, because it could be that you can calculate it, it'll twist 720 degrees, but once it gets to 300 degrees, it's actually yielded or even fractured. So yeah, they do kind of work together. Just because you can calculate one of them doesn't mean it is automatically going to do the other one. I'm talking about shear stress and angle of twist. All right, let's go back to our sheet over here. Actually, let's go to web work, because that's all there is to the equation, TL over JG. So let's go over here to web work and see if we can find a problem worth looking at. We did that one to end last time. Well, we've got our answers in there already. It does have a angle of twist associated with that one. Let's do this one. Let's do this one to start with. So let's copy this image, paste it over in our notebook, and let's go over here so you can see it. we'll have to put our numbers back in here. Let's see. L1, 1.8 feet. L2, 3.2 feet. T1, 110 kip inches. Remember, a kip is 1,000 pounds. T2, 45 kip inches. And I have two different materials. I have BC, so the one on the end, the free end, is magnesium. Let's see. And AB is annealed ENGR. So we'll have to look. I don't have any real idea what those modulus of rigidity may be, so we'll definitely have to look those up. And then we have some dimensions here. So the BC is a solid, and it is 3.4 inch outer diameter. And then this part, AB, has a 4.95 OD and a 2.45, these are inches, ID. So ID is inner diameter, OD is outer diameter. All right, so let's go look up our material properties because I don't know them. So I'm just over here. I'm going to have to zoom out to be able to see the names of the materials. All right, so we've got extruded magnesium. So it looks like that, which column? This very far column, 2.4 million PSI. So I'm going to write that down. And annealed ENGR, where would that be? There it is at the very bottom here, 8.1 million PSI. I made this comment one of the times. If you get these numbers and you've got, you realize, oh, I need the metric version, don't convert these over just with converting PSI to pascals. But at least don't do that for solving web work, or even a test problem could throw you off that way, because they're rounded a lot in the chart. So actually go to the other chart, find the number you actually need, just so that you don't have to worry with some pretty large rounding differences versus what the chart says versus what would actually happen if you took 8.1 million and converted it to pascals. All right, looks like we've got all that we need to work this part of the problem. So let's go back over here. And we're going to need two sections. So we've got section here, and then there's going to be a section here. And we have to have two different sections because each of those sections, they're going to have different torques, they're different materials, and they're different sizes. It only needs to be one thing different. It doesn't have to be all the things different to have to create a new section. In this case, all of the things are different, even the length. But it only has to be one that's different between to create a new section. So let's do the BC first. So the angle of twist for section BC is equal to the torque in that section, the length of that section over polar moment of inertia for that section, and the modulus of rigidity for that section. So the torque in that section, I'm not going to draw this particular, I'll draw the next one. I won't. This one is 45 kip inches. So that's 45. I don't know if MathCAD is going to know kips. We'll see. I might just put 45,000 inch pounds. I do have to assign this one a direction. So it doesn't matter. Well, let's see the problem. What does it say? If the shaft twists in the direction of T1, so kind of towards us, that is going to be a positive angle. So I'm going to give this section a negative one because it's twisting away from us. So this will actually be a negative. All right. And times L, 3.2 feet. There's some mixed units again that I'll have to deal with, but I'm going to let MathCAD deal with it. J, pi over 2 times, this one is solid, so it's only c to the fourth, which is 3.4 inches over 2 raised to the fourth power. There is a version of this equation where you can use diameters to the fourth, and you'll see that a lot in shaft type equations where it's often easier to use the diameter, or maybe not easier mathematically to use the diameter, but in real life, because if you go to measure something, if I go to measure the diameter of this pin, then I pick up some calipers, you know, are there calipers in here? I don't know. Yes. Pick up some calipers, and when I measure it, I measure the outside, I measure the diameter. You don't have a tool that just goes and measures the radius. So that's why a lot of these equations will be set up to use diameters just to make them more directly transferable to real life. In here, it's fine to just divide by 2 or whatever, but sometimes you'll see this with pi over 32 times OD to the fourth minus ID to the fourth. All right. G, this is the, which section? This is the magnesium section. So 2.4 times 10 to the 6 psi. And that will equal the angle of twist for section BC. So let's go over to MathCAD and actually calculate that. There it is. Why don't I just erase all of these so that I don't accidentally, carry over one of the units or one of the values from a previous problem. So our torque was 45, and we're going to see if MathCAD likes kips. I don't know. Kip inches. It does, so that's good. L was 3.2 feet. TL over J, which is going to depend on the C for this one. We'll do C, but there's going to be one for both of these. So these probably should have subscripts for signifying the torque and the length and the radius of just section BC. We're kind of taking a shortcut, I guess. C equals the 3.4 over 2. And then J will be pi over 2 times C to the fourth. And then G, the modulus of rigidity for this section, was 2.4 million psi. Oh, I didn't mean to do that. And then we'll calculate the angle of twist. So we will put a BC on this part so that we have a separate number here. T times L over J times G. Oh, keep typing over the top of stuff I've already done. TL, if I could type the right letter, over over J times G. There we go. There's our radian number. All right, let's go back over here and figure out what we need to do for the other section. So this other section, I will draw the free body diagram of it because it's a little bit different. So you've got the larger hollow section. We cut it open there, and then we've got the solid section BC that we just did. So here I've got a torque of 45 kip inches, and here I've got a torque 110, I think is what it was. Yes. Kip inches. And so that means I need another, whatever that difference is. What is that? 65 kip inches. Oh, slowing down. There we go. Yeah, that's right. All right. So here, this will be this angle of twist between point A and B. This one, maybe I should have drawn the first. Let's go back and draw the first one just to make one point on it. So it would have looked like this. I'll draw it up here in the corner. There's the 45. And there's the internal one, 45. So I gave that 45, the internal 45 going down, I gave it a negative sign. Here, the 65 is going up. So I need to give it the opposite sign. And it doesn't matter which one I give negative, which one I give positive. I just need them to have opposite signs because they're doing opposite things to the shaft. One's making it twist one way and the other's making it twist the opposite way. Now, the web work problem does specify that positive is what I've drawn as down. So this one I'm going to give so I've actually done them backwards, I guess. No. Yeah, because I gave the down one a negative sign, so I actually did it backwards, but we'll fix that at the end. All right, so we've got a 65 kip inch torque inside this section. The length of this section is 1.8 feet. The polar moment of inertia is pi over 2. I wrote the diameters out here, 4.95 and 2.45. So the outer one, 4.95 divided by 2 to get the radius, raised to the fourth, minus the inner one, I think it was 2.45, divided by 2 to get the radius. And then I have to multiply times. This was the annealed ENGR 8.1 million psi. Okay, so we need to solve that. Oh, let's write down our, what that would equal, I don't remember, 0.55. And again, it's probably 0.54 or something. Let's go to MathCAD and let's put in the values for this section. So I'll call these T1 just so that we have different variables. So T1 is it was 65 kip inches. L1 was 1.8 feet. TLJ is we need a C1 is 4.95 inches divided by 2. And we need a B1. We don't have a other B, but B1. It was, I don't remember, 2.45, I think. Yes. 2.45 inches, but divided by 2 because 2.45 was the actual diameter. So now we can do J equals pi over 2 times C to the fourth minus B to the fourth. And then, yeah, those need to be C1s and B1s, don't they? C1, B1. Okay, and this is, I guess, J1. And then we need our modulus of rigidity. Oh, hold up, I moved the screen on this, didn't I? All right, get back up there. There we go. G1 equals, let's see, what was it? 8.1 million psi. And then we should be able to do theta 1 equals T1 times L1 divided by J1 times G1. And we get another small number. Again, we're going to need to look at the more decimals than this, 0.003 though. And then the total angle of twist, theta total, we'll say, equals theta 1, and one of these Did I make them negative? I did not. So the one that's supposed to be negative is actually this one because of the problem statement. So the problem statement says that the positive direction is the way that this 110 number is going, which is going down in this side view. And so the 65 internal torque is actually opposing that, so it's the one that should have a negative sign, even though over on this page I drew them the opposite of that. So this is just for the problem statement to work out. So now I just need to add these two together. So I think I just called the first one theta. Oops, but let's go through there, theta, and then plus theta 1 equals, I must not have called it theta. What did I call it? Oh, I called it theta BC. Okay. So this other one might look better if we did AB. There we go. And then let's give this some more decimals. 051, let's look at that in degrees. 3 degrees. WebWork does want it in degrees over here. Let's see if it likes our number, 2.965162 degrees. Does not, oh, because it, oh, wait. What's it negative? If the shaft twists in the direction of T1, report a positive angle. Oh, if the shaft, okay. That's not what, I misinterpreted what it was saying there. So I actually had it right the first when I did it over here. Let's look at that. I actually had it right over here. So not there. I had it right on the written part. Had it right here. So if it twists in the direction of this, not if the internal torque is that direction. So if the shaft is moving in that direction, which that would be, these would be the correct signs. So we just need to put a negative sign on ours, and it should like that. And it does. Okay. All right. So that's about as complicated as these get, but let's look through some of the web work to see if there's something else that we want to work on. I don't know that there is, but let's look. This one's interesting because it is a design problem. It might be worth doing. Oh, and this is power transmission, which we won't talk about until next week. So let's look at this one and see if we want to do this. I think this one is probably worth doing, and then we'll finish this one and then we'll call it a day. So let's copy this image, paste it over here. Let's make it a little bigger. And then let me label up all of our stuff on here. So there's our image that we're working with. And let's just overlay some stuff on here from the problem statement. So the motor, so this little DC motor on the left-hand side supplies a torque of 6,000 Newton meters. Okay, so there's nothing here indicating which direction, so I'm just going to say that, turn it this way, 6 kilonewton meters. Okay, to the constant diameter annealed ENGR line shaft shown. So basically this, whoops, not that. This little guy is our shaft, and it is all a constant diameter, and it's all ENGR. So whatever this diameter is, at one point it's the same everywhere else, and it's the constant OD. It is solid. Yes, it is solid. It doesn't specifically say it's solid, but it doesn't give us any inner diameter data. So constant OD, and it's the, what was it, annealed ENGR? Yeah. Okay, so that's given. 3 machines are driven by the gears at B, C, and D. So I'm supplying 6,000 Newton meters, and then the 3 machines, they're geared, maybe a chain or maybe gears or whatever. It doesn't say gears, doesn't it? Yeah, it says gears. So these gears are connected to other gears that are not shown, and those gears are running these other machines. And the process of that, whatever is connected to the big gear B requires 2.6 kilonewton meters of torque. Whatever is connected to C requires 1.3, and whatever is connected to D, 2.1. Now I'm pretty sure if I add up 2.1, that doesn't add to 6. 2.6, 1.3, 2.1. Yeah, it does. All right. That 2.6, 1.3 plus 2.1 equals 6. So what that means is these little guys here, here, and here, these are bearings, and so they're kind of probably some roller bearings or something like that, or maybe journal bearings setups where they're supporting the shaft, but in our problem, they're not actually any source of loss. So they're completely frictionless, which is not realistic, but we're not to that point. That's a topic for much further down the line if you're mechanical engineering probably. So we're just going to assume that for the practical purposes, those that I highlighted green, the little bearings, are not really doing anything. They're just drawn so that the shaft isn't floating in the air. And then I'm applying or inputting 6 kilonewton meters, and I'm outputting a total of 6. It's just some of it's going to each one of these 3 gears. All right. What I want to find is the minimum shaft diameter required if the maximum shear stress, so tau max allowable, so tau allowable, is equal to 100 megapascals. So what that means is that in any piece of this shaft, the most stress I can have is 100 megapascals. Also, the angle of twist of D, which is over here, relative to A, which is over here, so basically between the input and last output. If all the intervals are 1.6, basically all the sections are 1.6 meters long. This is actually a really long machine. The shaft has a 73.5 millimeter diameter and is composed of annealed ENGR again. All right, so one of them we want to find the shaft diameter, and the other one we want to calculate the angle of twist if we know a certain shaft diameter. All right, let's do the tau allowable first. So this one is using our tau equals T times C over J, and again we're doing tau max. And this time we're saying that, well, tau max is equal to 100 megapascals equals T, the largest torque. Well, in this one, you've got the torque between A and B, the torque between B and C, and then the torque between C and D. The largest amount of torque is going to be between A and B because you're putting 6 kilonewton meters in right there at A, and then you're removing some of it at each successive stage, B, C, and D. But in this little section right here, that little section has to carry the entire 6 kilonewton meters. The next section carries 6 minus 2.6, and then the section between C and D carries the whatever that was, minus 1.3, and then the very last section from D to that last bearing block doesn't have any torque in it. So the worst case is this little yellow section. So where the T, the maximum torque there, is 6 kilonewton meters. We're trying to solve for the diameter. So the diameter is C. Well, the radius is C. So if I put D over 2 for C, then there's the diameter, over pi over 2 times, and again, c to the fourth, but let's look at that. So if I did, let's do it over here to the side, pi over 2 times c to the fourth, which is pi over 2 times d over 2 to the fourth. 2 to the fourth power is 2 times 2 is 4, times 2 is 8, times 2 is 16, times this 2 is 32. So pi over 32 times d to the fourth. Now I've got an equation with diameters in it, and I should be able to solve for that value for d. So let's go over to MathCAD, see if we can get MathCAD to solve this for us. I don't know if I can make it do that or not, but we'll find out. 100 megapascals. I'm going to do the control equal so I can do some symbolics on it. Equals T, which was 6 kilonewton meters, times D over 2. So that's T times C over J, which is pi over 32 times D to the fourth. And what I want it to do is let's go to math, symbolics. I want to just solve for D. I didn't test this ahead of time, so it might not like doing this. I don't know. It shouldn't be a big deal, but we might have to do it by hand. Sometimes, yeah, it looks like it got, oh, wow. Well, look at what it gave us. Well, these bottom two here are imaginary numbers, so it's not those. They have I in them, so it's definitely not that. So not sure why it didn't evaluate this as an actual number, but let's see what that equals. And let's put it in millimeters. 67.356 millimeters. That seems kind of large, but let's find out. That is correct. Oh, I didn't show you the web page. It is correct, 67 millimeters. That's a beefy shaft, but again, it's delivering 6,000 Newton meters, and it's I don't know how much it ended up being. It ended up being like 15 feet long or something like that. So it's a pretty decent sized shaft. So that MathCAD did not fail us. So that's good. All right. Let's go back to our other sheet. So from MathCAD, D was 67.355 millimeters. Okay, that's the first thing it asked for. The second thing it asked for is this relative angle of twist from point A all the way to point D, but not with this diameter. So it gave us a specific diameter of 73.5 millimeters. So if D equals 73.5 millimeters and G equals, it's the annealed invar, which is the 8.1 times 10 to the 6 for G. Oh, wait. That's the problem there. 8.1 times 10 to the 6 PSI, but we're in the metric system here, so I need to look up the correct value for the metric system. If I can get it to look at that. For some reason it wants to, oh, I'm in a different browser. That's why it's doing some weird stuff. Let's see. Rotate. Oh, I rotated too many times. There we go. So instead of these numbers over on this side, I want these numbers over here. I know it's really tiny on your screen. I just don't want to zoom in. Actually, I might need to zoom in to see it on my screen. I think it was 56 gigapascals. Yeah, 56 gigapascals, so 10 to the ninth. Had we converted the 8.1 million psi, we would have gotten somewhere near 56 gigapascals, but it would have been a different number. Okay, so now what do we need to do? This is a series of theta equations. Theta, A to B, equals 6. I'm going to, simplify these a little bit. So 6 kilonewton meters times the length. The problem statement says that the interval for each section is 1.6 meters. TL over J, which is pi over 2 times, well, let's just do the 32 so that we can do the diameter. 73.5, so there's C to the fourth, times our 56 gigapascals. And then theta from B to C is, let's look at our picture. In that section, I have to deliver, so I'm talking about this section here now. In this section, the green one, I have to deliver 6 minus the 2.6 that was removed from there. So what's that, 3.4? If you're unsure about where the 3.4 comes from, then, go here, draw the free body diagram in the middle of that section, section BC, and add up 6 minus 2.6, and you should get 3.4. The length is the same as the other one. The denominator is the same also. And then the last one, theta C to D, is carrying 2.1. So it's the 3.4, and then I removed 1.3 kilonewton meters at C, and so that last little section there just carries 2.1. The very last section carries 0. No torque in that last section. So I forgot the number. 2.1. 2.1 kilonewton meters, same length according to the problem statement, and same denominator. I left the units. Those are millimeters. That is important because some of these other units are in meters. Okay, and I would need to add each of these together. They're all going to twist in the same direction because they're all removing torque, so they're all opposing the 6,000 Newton meters going in. They're all opposing that, so that creates the same direction torque or twist on each one of those sections. So let's just put that in MathCAD. Maybe we can put it in MathCAD all as one big equation. Let's get a new sheet. So theta equals, and let's see, the denominator and actually L are the same on all of these, right? So we could probably simplify this. I'll keep it expanded though, I guess. So what was this number? 6 kilonewton meters times 1.6 meters. Oops, that's TL over pi over 32 times 73.5 millimeters to the fourth times what was our 56 gigapascals, I think. Oh, I did not type 56 gigapascals. Now we could, why don't we do plus, and then let's just copy all of this, paste it over here, and change the 6 to 3.4. right? And then we'll add another and change the 6 to 2.1. And then we will just ask it theta equals, WebWork wants this in degrees, so let's say degrees, 6.571. So let's put that into our 6.571, submit, and we got it right. We did round a little bit there, but it was happy with us, I guess. So these are, I'm doing these in MathCAD because the main issue with these problems is just making sure your units match up and you put all the numbers into your calculator correctly. So I'm offloading that little bit over to MathCAD. So they're definitely worth something to practice, mainly to make sure you don't make math errors, because the actual concept of it is pretty straightforward. I don't think there's something that's really hidden or confusing or anything like that. Maybe it gets confusing on what the internal torque is, but if you find yourself getting confused on the internal torque, then you know draw the free body diagrams, draw them out so that you can actually see what must be inside. If you know all the external torques, they have to balance. If they don't balance, you don't have as many going up as you have going down, clockwise and counterclockwise, or whatever you want to think of it as, then it's not in equilibrium, and that piece you drew is becoming disconnected from the piece it's supposed to be attached to if they're not in equilibrium. So try and draw the picture if you have trouble just writing them out like we did kind of on this last one. All right, so I'm going to end here. Next week we'll do some power transmission. And don't forget, I saw some activity in the Discord looking for teams, so that's good. Don't forget that you do have this other project kind of running in the background that you need to be working on in a team. So the teams are 3, maybe 4 people, 2 if you have to, but not one person, unless there's really some reason you have to have one person. So I will see y'all next week, and we'll do some power transmission.